Hi, in the last module on deterioration of embedded metal or the steel reinforcement in the concrete, we talked mainly about the how the steel, various types of steel can get corroded, corrosion mechanisms of different type of steels, etc. we covered. In this module we are going to talk about deterioration of the cementitious system or the plain concrete itself. So, this is the outline of this module, where we will talk about what are the essentials for a durable concrete system and then various deterioration mechanisms. In this particular lecture we will cover sulphate attack and biofouling and biogenic acid attack. In the coming lectures we will talk about freeze thaw attack, alkali silica reaction, shrinkage and creep, and also some other deterioration mechanisms such as or damage mechanisms such as fire attack, or what will happen to concrete at elevated temperature, and then also looking at erosion and some other mechanisms. Now, as we discussed in the previous module, a balanced approach is very much necessary for ensuring durable reinforced concrete systems and enhance the service life. Now, when I say balanced approach, it is to do with both the steel and the concrete. Here you can see on this balance on the left side, item number 1, we are talking mainly about the corrosion resistance of the steel, and the number 2 is mainly on the corrosion resistance, or in other words the degradation or damage of the concrete cover, which is necessary for preventing the deleterious elements to enter the concrete, which eventually leads to cracking and then corrosion of the steel. So, a synergetic effect need to be considered, both of steel and concrete. Now, when this is on the left side, you see a picture which indicates how a typical reinforced concrete system will look like. Over there you can see steel reinforcement, which is the black solid line, inside which, or the concrete inside that we can call hardcrete, and the concrete outside the steel reinforcement we are going to call it as covercrete. Now, corecrete or the hardcrete influences a lot on the strength of the reinforced concrete system, where the covercrete influences a lot on the durability of the concrete system. So, if you look carefully on the picture on the left side, you will see that the covercrete is of a different texture, basically to indicate that if you do not have a good concreting practice, you might have a very good hardcrete, but the covercrete might be still very porous in nature. So, what we need is something like on the right side, where good quality hardcrete and or corecrete, and at the same time good quality covercrete are essential. So, this is okay, this is not okay. Okay. So, this, and when you talk about this good quality covercrete and concrete, how do we achieve? It is possible by having good materials, good mix designs, and then very good placement procedure, and also adequate curing. All these are necessary to ensure good quality hardcrete and covercrete. And when you talk about concrete, the pores or the size of pores and how they are distributed in concrete is very important to consider. As in this picture you can see this size of these pores range all the way from 1 nanometer to about 10 millimeter. So, this is the range of different type of pores or voids that can be present in concrete, which might very well influence the rate at which different deleterious elements such as chloride, moisture, oxygen, carbon dioxide, sulphate, all this can enter the concrete. So, having a very compact microstructure is very important to reduce the rate of ingress of these deleterious elements through the cover concrete. So, that means you need to have very small pore size or very compact microstructure. So, how do we achieve this very or highly compact microstructure? We can use different type of chemical and mineral admixtures and adequate curing. I am emphasizing again on adequate curing, because it is not just having good quality materials and design procedures, but also at the after making the concrete, after placing the concrete, you need to have very good curing also. If you do not cure the concrete properly, you may not really achieve durable concrete systems. It is just like having different type of vegetables. You can have dishes made with same vegetable, but the way you make the curry or the way you make the dish is very influential on how at the end the taste of that dish would be. So, you can probably is a good analogy here also. In concrete we add different ingredients, mineral and chemical admixtures, then make them pack them very well, and then at the end you have to pack and then place and then cure the concrete very well. That is very much important to achieve desired workability, strength and durability. And essentially what is durability? It is nothing but strength in long term. So, one thing to mention here was this use of cement should be considered not as a filler, but as a binder. In other words, when we talk about mixed design, we should think about having minimal amount of cement which will play a role mainly as a binder or a glue to hold all the aggregate particles together. That should be the idea, because why I am saying that is, there are many cases where people say, okay, if you want to increase the strength, you go for more cement content, which is not the right thing to do always, because cement is the one which is probably most reactive element in the concrete. So, whenever we talk about long term chemical degradation, it is the cement which gets reacted. So, and thereby changes the properties of the concrete. So, if you have minimal cement, that is always going to be probably more durable concrete system. Now, what are mineral admixtures? First I would say what this mineral admixture, it is actually a common name used in India, but not outside Indian border. So, outside it is more technically correct name is supplementary cementitious materials or SCMs. So, I would like you to actually talk in terms of SCMs and not when you, especially when you start writing documents, we should really talk about SCMs and not probably the mineral admixtures. Now, what is a mineral, what is an SCM? A finely ground solid material that when used in conjunction with Portland cement contributes to the properties of the hardened concrete through hydraulic or pozzolanic activities or both. Now, what does it contain? It main ingredient which or the component which we are looking for in SCMs is the amorphous or reactive silica, which is in presence of water combines with calcium hydroxide to form calcium silicate hydrate, which is basically the glue which you are talking about when in cement hydration. Now, this reactive silica is very important to have, it is not just silica. So, when you talk about SCMs, you have to really ensure that that particular SCM has sufficient amount of amorphous silica. Now, here the first equation on the top of the slide, it shows a typical Portland cement hydration reaction, where you can see C3S and C2S are the reactants, along with water they form CSH and CH. Now, when we talk about these SCMs or pozzolanic reaction, we are essentially talking about using this calcium hydroxide which is formed because of the cement hydration reaction, and that calcium hydroxide reacts with, so this calcium hydroxide reacts with the amorphous silica which is present in the SCM, and when there is sufficient water or moisture, it forms more CSH. Now, the CSH is formed by replacing, or it is actually forming by consuming calcium hydroxide. So, the space which was occupied by calcium hydroxide is now going to be occupied by CSH. So, that enables it to form a more compact microstructure which is more strong also and durable in most cases. Now, so the outcome of this entire discussion is the use of SCMs and low water binder ratio and sufficient quantities of super plasticizers, and then also good placement and compaction procedures and adequate curing. All these if you are ensuring, then it is very easy to achieve highly compact microstructure and thereby high resistance against the ingress of deleterious elements through concrete. So, we can have durable concrete. So, let us say look at, I am going to show you one slide on water binder ratio, one slide, two slides on SCMs, how they really influence the rate of ingress of these deleterious elements. If you are talking about water cement ratio, when you have a very low water cement ratio, the chance of having pores or micropores is very less, which is this case here. So, you can see that in the picture I am not really showing any micropores, whereas in the second picture on the bottom right with high water cement ratio. So, whatever the amount of water which is not used in the cement hydration reaction, it is going to be now left it will be unused water which eventually dries and leave a air void. So, this white circular or elliptical shapes which I am showing there is all indicating that there are possibility of more air voids in the concrete when you have a higher water binder ratio. So, what we should do is we should use lower water binder ratios, and if the water binder ratio is low, if it is in leading to workability related issues, then you are handle that by using chemical admixtures such as super plasticizers and not by adding more water. So, the point here is when you have higher water, when you have a lower water binder ratio, your diffusion or the rate of diffusion or ingress of various chemicals into the concrete is going to be less. You can see that on this graph. Now, when you talk about fly ash or slag, which are the two widely used supplementary cementitious materials, again we can very clearly see at 28 days you might not see, or until 28 days you might not see significant difference between the diffusion coefficient of PC here is the OPC or Portland cement, ordinary Portland cement, and then there is not much difference in the diffusion coefficient of ordinary Portland cement based concrete or concrete with slag or fly ash replacement. But as time passes, if you see on the it is a log scale, on the on the x axis or abscissa. You can see that definitely as time passes the diffusion coefficient of slag and fly ash is significantly less than that of ordinary Portland cement concrete. So, definitely in the long run you can because the concrete continues to hydrate and then make more and more CSH, and then effectively you get more and more compact microstructure as time passes, which leads to reduction in the rate of ingress of different elements into the concrete. Now, if you are talking about silica fume, which is also a very good SCM with very fine particle size. So, the silica fume has a dual role, both as a pozzolanic material and at the same time it also have a little bit of filler effect depending on how much silica fume is used. As you see in this photograph or micrograph here, you can see that cement particles are much larger than the silica fume particles. So, all the space between these cement grades can probably get filled, or the very fine pores available can also get filled by the silica fume particle depending on how much is the dosage. Definitely you can see the rate of ingress is going to be less when you add silica fume. Now, we also talked about chemical admixtures. I am showing here 6 widely used chemical admixtures. First one is super plasticizer, which is used mainly for handling the workability related issues, and then you have an air entrainer number 2, which is which also helps in enhancing the flow properties, but at the same time it is also used widely for addressing the freeze thaw attack in concrete structures. So, you introduce small air bubbles, as you see in this picture, these small black circles which are all air bubbles introduced into the concrete by this air entraining admixtures. So, they help in providing sufficient space for during the winter when water gets into the concrete, it starts expanding and try to become ice. So, during that expansive stresses, if there is no air voids, then you will have significant expansive stresses. So, that can be avoided by providing these small air bubbles in concrete. We will talk much more in detail in the next lecture on that. And then you have retarders, which is mainly to slow down the reaction rate, especially for cases like what you see in that picture. It is a concrete truck stuck in a traffic. So, if the concrete has already started mixing and or hydrating, and then you are stuck in the traffic and you have time to reach the construction site. So, the best thing to do there is to reduce the rate of reaction, so that you can still have good concrete by the time you reach the construction site. Now, number 4 over here is the corrosion inhibitors, which are mainly used to control or to enhance the corrosion resistance of the steel rebar or the steel concrete system. What it does is, while mixed with concrete, it actually helps in providing a better passive film or a more resistant passive film. So, my point to note here is, these inhibitor, they will come into action maybe after a decade or 2, depending on the corrosive environment, how corrosive the environment is. Now, shrinkage reducing admixture this is number 5. Shrinkage reducing admixture, especially when the concrete can be more prone to cracking or very thin elements which can be more prone to cracking. So, we tend to use shrinkage reducing admixture. And number 6, which is an accelerator. An accelerator which is mainly used when you talk about very low temperature or cold climate, where you want the concrete or the cement to hydrate faster. So, you tend to use, we can use accelerator. There are different type of these admixtures available to cater to different requirements of the concrete. Now, one thing is, this quantity of these admixtures which are added to the concrete is very small. So, to attain uniform distribution or making sure that these admixtures are available in the entire concrete in a uniform manner, it is recommended to add these admixtures to this water and then use that mixing water rather than adding directly to the concrete being mixed. Now, the ASTM C494 provides typical guideline specifications for typical chemical admixtures. Now, main advantages of using these admixtures to achieve and enhance certain desired properties in both fresh and hardened stages, like for fresh state, superplasticizer, air entrainer, retarder and accelerator, all these are mainly handling the properties during the fresh state, whereas corrosion inhibitor and shrinkage reducing admixtures are mainly for the hardened state. And depending on what type of shrinkage, whether you are talking about plastic shrinkage or later. Then, to ensure quality during the stages of mixing, transporting, placing and curing in adverse weather conditions, and to face emergencies during site operations. This is one emergency which we briefly discussed. And then to reduce the overall cost to achieve the same desired properties to ensure durability. How do we, why we are saying overall cost is because when you talk about these admixtures into the concrete, the unit cost of the concrete might increase slightly. However, you have to think about the entire system, and if you really look into that, basically by you will end up in having a peaceful concreting to that manner. matter. So, definitely the cost, overall cost is going to decrease, because you will not have much of hassle in placing the concrete, and at the end you will get a good product. So, essentially the cost, overall cost is going to be better. Before getting into the various deterioration mechanisms, I would like to just tell you about these other courses which are offered through NPTEL from our group: Modern Construction Materials by Professor Gettu, Advanced Concrete Technology by Professor Manu Santhanam, and then Advanced Topics in Science and Technology of Concrete, where we have collected lectures from multiple experts from all over the world who have visited us. So, we requested them to give a couple of hours of lectures in their topic of expertise, and all that lectures are collated, and then nice topic, especially for research scholars and researchers. This course is very useful. And then also another course on characterization of construction materials by Professor Manu Santhanam and Dr. Piyush Chonsali. Now, looking at various deterioration or damage mechanisms in concrete systems, main thing which why we are worried about is, if the concrete gets damaged, eventually it affects the steel inside the concrete, and then it influences the structural capacity of the system. So, we already talked about how corrosion happens, mainly due to carbonation and chloride attack, and when we talk about the concrete, we are going to talk about abrasion, erosion very briefly, freeze thaw attack and fire, and then also alkali aggregate reaction or alkali silica reaction, acid attack, sulphate attack, fouling, or basically again acid attack. So, all these we will be discussing. For first we are going to talk about sulphate attack. There are two types of sulphate attack depending on the source of the sulphate. It is external and internal sulphate attack. The major mechanism, I am just showing three pictures here. On the left side you will see what happens at the microscopic level. You have this formation of these needle shaped ettringite crystals in whichever wherever there is a little bit of space available, it forms, and the volume of these ettringite needles are actually more than the reactants, which eventually leads to expansive stresses, which induces cracks like this, as you see on the second picture. You can see this this is an aggregate, and then this is the cement paste. And you can see significant cracking all along the cement paste and along the boundary, or the boundary between the aggregate and cement paste, or ITZ. So, the system does not really is not really an integral system when you have significant cracking like this. And on a larger scale, this is a third one is a picture of a bridge, where you can very clearly see a lot of cracking in that region, that column or the pier which you are seeing. So, from microstructure to macro level cracking, it really leads to significant distress of the structure. So, it is a major deterioration mechanism which we all need to know and worry about, so that we can design our structures to prevent them. Now, here I am showing some examples of how this external sulphate attack, not the internal. This picture mainly shows about external sulphate attack, where over here you can see this is a concrete element which it's degraded exactly where it is coming out of the soil, and here also you can see where it is in touch with the water, you have degradation. Here also you can see when it is in the region where it is in contact with water, it is almost completely gone. I mean, there is no more concrete left in that section element. And one thing to note here, you can see this close up of that concrete element with a small pen to give you an idea about what is the size. You can very clearly see that the aggregates, which are basically river gravel, I think it looks like. So, the rounded aggregates, they are not damaged, they are intact. However, the cement which is in between the aggregates, which are supposed to glue the aggregates together, are almost lost or completely degraded. So, definitely a clear indication that it is cement which is getting at, or the hardened cement paste which is getting attacked and not the aggregate. So, if you reduce the amount of cement, again it is going to be easier to resist sulphate attack. Now, here on the bottom image you can see the water cement ratio of 0.65 and water cement ratio of 0.39 or let us say 0.4. So, what the one with 0.4 or 0.39 is highly resistant against sulphate attack as compared to the one with 0.65 on the left side, and you can also see that both are using type 5 cement, and and also you can see this on the left side that much degradation happened in 12 years, whereas on the right side this much degradation, only that much degradation happened and in a longer time, which is 16 years. So, even after exposing the concrete for longer period of time, when you have a lower water cement ratio, definitely the amount of sulphate in sulphate attack is going to be less. So, now let us look at what are the different sources of sulphates. As we saw in the previous slide, definitely there are sulphate rich soil and sulphate rich groundwater or water bodies present next to the concrete structures or in contact with the concrete structures, and also depending on the type of structure we have to see whether there is any agricultural soil or water adjacent to the concrete elements, and then also effluents of furnaces and effluents from the chemical industry. These are all other sources where you will have significant amount of sulphates present, and if they are coming in contact with the concrete element, that element is vulnerable to sulphate attack and further deterioration. Now, the bottom line of this slide is that it is not that difficult to find high concentrations of sulphates in either soil or water body which is in contact with the concrete structures. So, you have to really think about this and make sure that the type of concrete which you are using is sufficiently resistant against the sulphate attack for that desired life which we are talking about. Now, as we mentioned earlier, there are two types of sulphate attack, one is external and one is internal. In the external sulphate attack, first step is the sulphates from this either water or soil body will enter the concrete. So, now then they become internal to the concrete, and then second step is once they enter the concrete, which is this, once they enter the concrete it reacts with the calcium hydroxide which is present and forming gypsum. Now, that gypsum will react with the in step 3, that gypsum will react with the monosulphate which is present, and this conversion of this monosulphate into ettringite will happen. Now, this conversion is the dangerous part there, because there is a volumetric expansion, because ettringite will consume more space or will need more space than the combined volume of monosulphate and gypsum, and it leads to cracking of the concrete because of the expansive stresses. So, here you have a product which is having more volume than the reactants, definitely that will induce stresses in the entire matrix of the concrete and eventually leading to cracking. So, how we can toward the right side of this table, how we can actually control this. The first step we can control by increasing permeability, by reducing the permeability of the concrete cover, either by using low water cement ratio or by using SCMs, and if in the second step that can be controlled by controlling the amount of calcium hydroxide. If you have lower calcium hydroxide content, then definitely the amount of reactants is less, so the amount of gypsum formed is also going to be less. So, again that can be achieved by using pozzolans or SCM, and in the third step, as you see here in the monosulphate phase you have C4A. So, definitely if you have less amount of C3A in your cement, again we are controlling the amount of reactants. So, the amount of this monosulfate phase which is available is going to be less if you have a low C3A content cement, which is a type 2 or 5 cement, but essentially it is the C3A content which we are trying to reduce. So, type 2 is the cement with about less than 7% C3A, and type 5 is cement with less than 5% C3A. Now, this is a graph showing how this amount of C3 or the C3A content is going to just a demonstration of that. Let us say you are talking about concrete with 0.5 water cement ratio, or let us pick 0.6 water cement ratio. Here as you see, if it is type 1 cement you have this much expansion, if it is type 2 cement you have this much expansion, and if it is type 5 you have this much. So, definitely there is a reduction. Type 1 is 7%, more than 7%, type 2 is more than, or 5 to 7%, and type 3 is less than 5%. So, as the amount of C3A is reduced, definitely the amount of expansion is less. So, definitely if you are talking about sulfate resistant concrete systems, we have to go for cements which are low, which are having low C3A content, and of course lower the water cement ratio, so that the entire pore structure is better refined, I mean less available less amount of pores are available. So, the effectively you use low permeability concrete. Now, internal sulfate attack, where we are talking about some issues related to the time at which these ettringites are formed. So, for example, what happens in especially in terms of hot weather concreting or mass concreting, where the heat generated is significantly high, which leads to a curing temperature or early temperature of more than 70 degrees Celsius. If that happens, then the normal formation of ettringite will not happen. I am going to go to the next slide and to show you what is this normal formation of ettringite. So, here you can see this curve here, which is this one, which goes like this, that is the curve for ettringite formation, and you notice that about this time, about after a few hours of concrete, once the concrete is mixed, after few hours there is a increase in the amount of ettringites which are formed, and they occupy their space because at that stage the concrete is still somewhat plastic, so that they can occupy that space, and it is not completely hardened or not completely set also. So, at that time it occupies the space without creating any damage to the concrete. But when you have this high temperature of greater than 70 degrees Celsius, and then this ettringite is not stable and it does not form, and what happens is it does not form at that time and does not occupy the space required, but after several years or decades, when sufficient amount of the reactants which we were talking about earlier, moisture is available, these monosulfates might get converted to ettringite at a later stage. So, we call it delayed ettringite formation, just because it is not happening during the early curing period, but it is happening at a much later stage. Now, this when it is happening at a delayed time or at a later stage, you will have, because the concrete, this concrete is already hardened concrete, and there is no reserved space for this ettringite in that concrete, because it was not reserved in the early stage. So, it generates a tremendous expansive stresses, which leads to, first it will occupy all the space between the aggregate and the cement paste, and then eventually try to exert tensile stresses or expansive stresses, which lead to significant cracking. So, this is the problem with delayed ettringite formation, because that space required is not originally reserved, and when it forms at a later stage, it does not have that space, but exerts the significant expansive stresses, which leads to cracking. Now, this already we discussed. So, you can see here that cracking, you can see significant cracking here in the aggregate faces also, and these are all the needle shaped ettringite which are occupying the voids available within the concrete system. Now, this is some demonstrations of this sulphate attack. You can see these are bridge piers, very large bridge piers. So, definitely these are mass concrete elements. So, probably the curing temperature might have reached a level which is beyond 70 degrees Celsius, and after long period of time they started demonstrating or started degrading or deteriorating due to sulphate. You can see a significant cracking here, a lot of cracking all over the place on this concrete elements. So, significant cracking especially for mass concrete elements, we have to really think about this. Okay. Now, here is some more examples where you can see map cracking. There is no particular shape for these cracks which are formed due to sulphate attack, and here also you can see random cracking on all these elements. Again, all these are mass concrete elements, and that is where we see maximum delayed ettringite formation, internal sulphate attack. This is a table which shows a study done on various bridges in France. A main point to notice here is the maximum temperature which is in this one, the blue box. You can see that they are all actually above 70 except one which is 69, but we can say for all practical purposes they are high temperature, which is probably not good, and also the amount of C3A which is in the cement which was used is very high, more than 7% C3A. So, these are all leading to significant internal sulphate attack. Now, how to prevent? This is the nutshell, and we have to use low curing temperature or make sure that the temperature during the curing period is less than 70 degrees Celsius, and concrete should have low permeability. By using SEMs or good mixed design practices, we can achieve low permeable design and curing practices, we can achieve low permeable concrete, and also the cement which we use should have low C3A content and definitely less availability of water. So, if we are able to achieve these, then we can definitely prevent sulphate attack. Now, the next damage mechanism or deterioration mechanism we are talking about is biofouling in concrete structures. Not really given much importance to it, but this is again, I mean, we thought we should include and give some light on this type of deterioration which happens on concrete structures. So, as you see here on the picture, you can see a nest of an octopus on the soffit of concrete anchor. So these are the nice resting place for these microorganisms. So, what is there in concrete which which is attracting these microorganisms to get attracted to the concrete elements? So, we will see on the next slide what is some more pictures or photographs showing different type of biofouling. So, the first picture, this repetition actually here, anyway. This you can see here, it is a bridge column. I had another nice picture here of bridge of port structure, a bridge in a port where again significant fouling was there. Anyway, it is okay. It is also, this picture is also giving similar message, and you can see here significant surface damage on these concrete elements. You can see here, all these are actually concrete surfaces getting damaged because of biofouling. This is again microorganisms, how they interact with various building materials. I am not going to go much detail into this, but as a civil engineer we should know that these microorganisms can also actually damage concrete elements in the long run, and we should keep away these microorganisms from the concrete surfaces. And how do we do that? We will see towards the end of this lecture. And this is again another picture showing again this is okay. So, the main damage mechanism here is few minutes ago I said why are they attracted to this concrete structures. So, all algae or these microorganisms, they consume calcium, aluminum, silicon, iron, etc. for their metabolism. Now, concrete we have all these available. For example, in your cement you have calcium, you have aluminum, you have silicon, and you have iron, oxides of these are available in our cement or hardened concrete systems. Now, what happens is these metabolic actions, it involves production and release of organic acid. So, essentially these lead to acid attack of concrete surfaces, that is a key message here. Now, other examples where similar acid attack is witnessed or observed are like effluents from the agriculture and agro food industries, where all the effluents might have significant amount of acid or acids which is actually thrown into, or the concrete structures nearby will get exposed to these acids. And what do? They bacteria and yeast, they can degrade the organic compounds and produce organic acids, and fungi can also damage concrete and stone, even stone, by slow penetration into the surface. So, there are a lot of if you Google, you will see a lot of pictures showing these kind of long term deterioration mechanisms. And now, deterioration of concrete due to inorganic acids. Here you can see household and certain industrial waste, they contain organic matter that if not kept cold, because the temperature also matters a lot, will start to break down or biodegrade. So, bacteria will eat and digest the organic matter and then throwing away, or their excreta might be acidic in nature. And then you also have formation of sulfuric acid, formation of hydrogen sulfate, mainly depending on the amount of oxygen available. So, it depends whether it is a closed system or an open system, depending on that the amount of H2S or the type of H2S is also matters. Now, here you see the picture on the left side, it is inside view of a concrete manhole, on the right side inside view of a sewer pipeline. Okay. So, these are why I am showing these pictures, that this is major infrastructure systems where we tend to repair these systems very frequently, mainly because of this acid attack or H2S. Okay. So, let us see how the deterioration of concrete happens, mainly because of the inorganic acids, especially in sewer pipelines. So, we will look at that mechanism alone here. So, think about this sewer pipeline. So, H2S is produced, and then what will happen is this H2S, because it is heavier than air, it will try to settle right above the water body, and then because of the convection, possible convective currents, it will actually get circulated inside the airspace available or air fill cavities which are present on the concrete surfaces, and then they eventually redissolve in the water or slime, which the slime, if I draw a picture here. So, if this is the water body, and then you will see a lot of slime formation in this right here. So, and then they get adhered to the concrete walls, and then hydrogen sulfide, it forms a weak sulfuric acid, and this weak sulfuric acid attacks the concrete directly, especially that happens right here at the crown of the pipeline. It will directly attack the concrete and then lower the pH of the concrete from about 12 point, this I am missing, from about 12 plus to about 9. And now we all know that when the pH is about 9 or that low pH, the steel is very vulnerable to corrosion. So, that is what we have a significant problem of this corrosion of this pipelines or sewer pipelines, and their life is not really very long, even though we desire it to have. So, this picture on the left side actually shows how this entire mechanism, this sulphate attack mechanism is in a pipeline. And the point here is poor quality sewer pipelines usually get deteriorated in about 5 years. This is data which by talking to various people in the industry, they say mostly they replace or they get damaged in about 5 years, whereas the design life is about 20 years. So, how do we ensure that these infrastructure systems, and main thing is this deterioration happens below ground. So, we do not really see them happening on a regular basis. So, that is a major challenge in identifying what is happening and then really making sure that they do not really fail, and before that we are either replacing or repairing the structure. Now, different repair strategies for existing concrete systems, especially when we talk about this biological attack is what I am talking about here. Now, one is power wash, basically clean and then use good quality repair material and then use good quality surface coating. On the picture on the bottom left you can see power washing, but of course you have to really think about what is the pressure to be used for, and also it is good for when you are talking about large surface area, otherwise it may not be really economical. And then repair materials, top right image you can see good quality repair materials, and then the surface coating, a nice coating with a smooth finish will definitely help in preventing this biological attack. Now, power washing, you can see here on the picture on the left side, it is nicely cleaned. It is again this picture is need to be replaced. Okay. Yeah, power washing primarily done to avoid slip hazard, and it can start a devastating vicious cycle, because if you are actually going for very high pressure and high velocity, it may actually dislodge the aggregate particles also, or the cement particles at the near surface also. So, you have to really think about what is that power, the pressure which we need to use. So, an optimal pressure is very important to decide before we go for power washing. And repair materials, and again selection of the repair materials is very important. So, see here there are different materials available. This is just a simple table which I got from the internet. You can see the resistance of these different coating materials. So, all these are different coating materials, and these are the chemical resistance against what type of material. So, you can see that there are the resistance is varying from coating material to material, behaves in a different way. So, you have to really think depending on the type of exposure conditions you might have, which type of coating material have to be picked. Now, another thing is how smooth the surface of the repaired surface should be. So, here it is a picture showing R1 is the roughness 1 and R2 is a third level, or more rough surface. And if you look closely on these 8 photographs which you have on screen, you can see that from on the first row you can see which is surface with less roughness. You can see that the amount of green spots which you see is much less as compared to that on the second row, which is R3 or a more rough surface. So, you see in 19 days in the row 1 you have some spots forming, but in row 2 you have more green on 11 day itself or even before. But when you look at 25 days you can see that on the second row it is completely green, and in the first row you still have a significant region which is not attacked. So, definitely surface, how rough the surface is, definitely it plays a role on resistance against biofouling. Now, the question is, does this mean that all the exterior surfaces should be smooth? Maybe no, because you have to see this is, if it is smooth, maybe for a wall element it may be okay, but if you are talking about a floor where you also walk, you may not want it to be very smooth, because people will slip, it will be a slip hazard. So, we have to be again all these techniques whatever we talk, you have to really think about where you are applying, for what specific conditions or specific applications, and you have to also think about multiple damage mechanisms. And it is not like you look at only one thing and then forget about the other damage mechanism. So, you have to think holistically when we decide about what type of deterioration and how to prevent. Now, again one more thing, last thing to talk about is acid attack. Calcium aluminate cement have been proven to be highly resistant against acids. However, I am showing this picture here, the one on the left side is showing a calcium aluminate cement and the one on the right side is showing Portland cement. Very clearly the one on the right side is more degraded. So, we can conclude that CSC cements are more resistant against acids. However, there are publications which say in some cases you might have different, or the resistance might vary from case to case or from acid to acid. So, you have to really look at what type of acidic conditions you will have, and then accordingly decide on the type of cement used. And this is also another from the same literature, this is another case showing that the Portland cement system will have much more weight loss or more degradation as compared to CSC systems when it is exposed to acids. Now, nowadays you also have a lot of these pipes which are coming with interior coatings which are very highly resistant against various types of acids. So, again the products are available, you have to really make sure that the tender specifications which we make are actually looking for some measurable parameters which will really give you long life as desired. And if you do a good job in homework, a good homework in framing the tender specifications, I think most of our constructed facilities will last really long. But most of the time we fail there, we do not really put in enough time in planning or in making these tender specifications, thinking about what could go wrong and how do I prevent from that from happening. I think towards the end of the course we will have one lecture exclusively on designing tender specifications. So, by the end of the course you will be better prepared to handle such situations and really be able to durable systems, construct durable systems. So, it is a summary. Mineral and chemical admixtures can be used to get a good quality concrete, especially cover concrete, and then susceptibility and effect of sulphate attack, acid attack etc. can be reduced by understanding the mechanisms, how they really happen, and understanding what type of exposure conditions you have, and then addressing those factors, coming up with a good tender specification or good measurable parameters for the type of system which you are designing, mainly to take care of, to prevent such deterioration from happening during the design life. And as we always say, prevention is better than cure. So, the idea should be make good concrete at the beginning itself, and then for that we have to select good materials, have good mix design, good placing procedures, compaction, and then cure the concrete adequately. All these are very much necessary, and if we do all this we will definitely have long lasting beautiful concrete structures. Now, next this is the list of references which have been used to make this particular presentation. Thank you.